And I'm presenting first today, so I'll share my screen. Okay, so our first topic for today is going to be the Arrhenius equation and catalysts in general. So for the first part of this, I want to give sort of the big picture overview as to why studying the Arrhenius equation is relevant in the first place. So this is the form of the Arrhenius equation as it was introduced in lecture. So K is the rate constant for the reaction, which is the thing that you would measure if you were keeping track of reactants and products as they change over time in a reaction. A is a pre-exponential factor, and the EA term represents the activation energy. RNT are the gas constant as well as temperature. And the reason why this equation is relevant is that if you were able to perform multiple kinetics experiments at various different temperatures, as seen in a graph like this, where essentially what you're doing is just recording the rate constant at different temperatures, then you get this equation of a line that comes from taking the natural log of this expression here. And if you solve for the intercept, you get the natural log of the pre-exponential factor. And with the slope, you get the activation energy divided by R. So the reason why we study the Arrhenius equation is because the activation energy and the pre-exponential factor are pretty important parameters for a reaction, especially when we're trying to understand enzymes and their role in catalysis. So in the end, this is what we're working towards, getting an intuitive understanding for what A and activation energy mean, and then being able to read a graph like this to determine them, or just by using this equation to learn about the reaction and how an enzyme might be functioning within it. So first, to get an understanding of activation energy and pre-exponential factor, the first thing I wanted to discuss is what are the things that really determine a reaction rate. And so if we're considering a reaction model in which you need multiple molecules coming together to collide in order to react, as is the case for something like ATP hydrolysis, which you can see right here, which requires like a water molecule colliding with the gamma phosphate, I believe, of ATP and cleaving it. Of course, the first thing that you need in order for this reaction to occur is the molecules have to actually collide. And then after the collision occurs, it's not just sufficient for there to be a random collision. You need the collision to occur in like a very specific orientation. So for example, if this water molecule collided with the nucleotide base of ATP, the reaction wouldn't progress. And furthermore, once you have this molecule or the two molecules colliding in a very specific orientation, you also need them to reach a high energy state called the transition state. And there needs to be sufficient energy for them to reach the state and eventually for the reaction to go to completion. So these three components are pretty important in terms of determining reaction rate. So starting with the first one is this idea of the collision rate and also how the diffusion limit plays into this. So if you think about two molecules in solution, this red and blue molecule, because of diffusion and essentially random motion, they might take a path like this before they eventually collide. And the rate at which that they're colliding is given by end collisions, or at least that's the way that we'll keep track of it for this model. And so as you would imagine, the number of collisions or the rate of collisions is related to the concentrations of the molecules, of course, because if you have more molecules, then you're more likely to get more collisions. And furthermore, there's also this idea of this upper bound on how fast the molecules can move through the medium, which is the diffusion limit. And in the case of water, it's about 10 to the power of 10 at 298 Kelvin. So this just gives you the limit for how fast molecules can actually move through the medium and collide. And that's ultimately what determines the maximum rate of collisions that are possible. And kind of just as a side note, this is not really relevant for the course, but just for your own knowledge, there are actually some enzymes that are called perfect enzymes in which they catalyze the actual reaction faster than the substrates can be brought to them by diffusion. So they're a pretty interesting class of enzymes. But as we mentioned before in our discussion of things that determine the reaction rate, not every single collision is going to lead to a productive reaction happening, or not even every collision is going to be in the proper orientation in order for the molecules to even have a chance of reaching the transition state. And so that's why there's this notion of this FP that comes into play, because this is essentially our way of saying there's only a certain fraction of the actual collisions that are going to be productive. And that's what essentially defines the pre-exponential factor. So you can think of the pre-exponential factor A as essentially just a measure of like how fast collisions are happening times the fraction of collisions that actually have the potential to be productive. And so after we've determined this pre-exponential factor, there's another layer of complexity or another requirement essentially to add on to this analysis of activation energy. as well as reaching the transition state. Because for all the molecules that even are in the proper orientation and collide successfully, not even all of them will reach the transition state because there is an energy gap. And to kind of analogize this, I have this really short diagram of an SN2 reaction, which you've probably studied in organic chemistry. And so, as you recall, in order for an SN2 reaction to occur, you need the molecules to collide in a very specific orientation. And even when they do collide in this very specific orientation in which the nucleophile is approaching from the side opposite to the leaving group, in order for this reaction to actually progress into the products, it necessitates the formation of this transition state, which is pretty high in energy. And the reason for this is because this orbital that was normally making a stable bond between the carbon and the bromine, now it's doing this weird thing where it's forming a sort of half weak bond with the nucleophile and another half weak bond with the bromine. And of course, this is like not a rigorous description at all of what's happening to the orbitals, but this is just sort of to give you an idea as to why a transition state is higher in energy. It's because the orbitals that were involved in previously really stable pairings now have to do this weird thing and to reach this very short-lived transition state. And that's ultimately what puts this at a higher energy. And also, if you recall from an earlier point in the course when we talked about the Boltzmann distribution, which essentially gives you the relationship between the energy difference between two populations of molecules, if you have n molecules at a zero energy state, then the number of molecules that you would expect at an energy state that is delta U above that energy state would be given by the Boltzmann distribution. So now we can bring together these two ideas. This notion that the transition state is some activation energy higher than where your reactants are, and also this idea that there's only a certain population of molecules that are even in the correct orientation to begin with to facilitate a reaction, to bring everything together into the Arrhenius equation, which is taking your A, the number of molecules that have the potential to react, and then this exponential term, which gives you the actual number of molecules that will reach the transition state. And this is the Arrhenius equation, just as you had seen in the previous slide. Are there any questions at this point so far? Okay. And so next, after discussing the Arrhenius equation, I think this kind of naturally leads us into a discussion of specific mechanisms for enzyme catalysis to occur. So we know that enzymes, when they catalyze a reaction, they typically increase the rate constants and make them go faster. And so these same principles that apply to things that govern the rate of a reaction also kind of constrain the degrees of freedom in which enzymes can speed up the reaction rate. And so the first part of how enzymes can do this refers to the pre-exponential factor and affecting like the fraction of collisions that are productive. And one way that enzymes can do this would be an example such as this. So if you have two substrates like the blue and the yellow one in this case, in order for them to successfully make this product, they would have to collide in a very specific angle or orientation. However, by having this enzyme here, after one of the substrates binds, it is essentially locked into place. And what the enzyme can do is even position the substrate in a way that it is most favorable so that when the second substrate binds, the reaction will be very productive. So that is one way that enzymes can speed up catalysis. And another way that enzymes can increase the reaction order, that can increase the rate constant for a reaction is by stabilizing the transition state, which effectively lowers the activation energy. So in this graph over here, this is the energy diagram for what essentially is a dipeptide that's being broken up into its two individual component amino acids. And of course, the way that this reaction proceeds is you need to have attack on this carbonyl with a water molecule that produces this unstable transition state. I hope you all can see it, but it's a negatively charged oxygen, which is unstable because of this free charge. And that's why you have a higher transition state. But what an enzyme can do is that in the pocket corresponding to its active site or its binding pocket, by having lots of residues that have hydrogens or lots of residues that are positively charged, then by essentially providing the counter ion to this oxygen, you can stabilize it and decrease the energy of the transition state, thereby allowing this reaction to proceed a lot faster since the activation barrier is lower. There's also another way that enzymes can speed up reactions, and that's to just alter the mechanism of the reaction as a whole. And I think this is something that you will probably discuss in lecture tomorrow. It's called the catalytic triad, and there's a family of proteins called serine proteases that have these three amino acids that just through clever acid-base chemistry can speed up this reaction, and serine actually participates as the first nucleophile as part of this reaction. but you'll see that in lecture hopefully tomorrow. And then lastly, I just wanted to go over a quick worksheet question that just goes over how to use the Arrhenius equation. So here is the problem. Suppose you measure the rate constant of a reaction at 300 kelvins to be 5 millimolar per second, and that's without enzyme catalysis. And then with enzyme catalysis, it's now 100 millimolar per second. So assuming that there's no change in the exponential factor caused by this enzyme, the pre-exponential factor, by what amount does the enzyme actually lower the activation energy? And I guess I'll just really quickly go over the solution for this. But essentially, the thing to do is to make two equations corresponding to the information that you do have. So the Arrhenius equation is essentially K is equal to A times e to the negative activation energy divided by RT. And so you plug in all the information that you know, and that gives you two equations. However, we still don't know what the pre-exponential factor is, or what the uncatalyzed activation energy or the catalyzed activation energy is. So we can take the natural log of both, and simply by just subtracting the two, since we're only interested in knowing by what amount the enzyme lowers the activation energy, we do the activation energy of the uncatalyzed reaction minus the activation energy of the catalyzed reaction. And hopefully I did this math correctly, but I think you should end up with that the activation energy is lowered by 7.5 kilojoules by this enzyme. So that's about all I wanted to go over today. Does anyone have any questions about what I talked about? Okay, well, in that case, I'll hand it over to the next tutor.
Hello. I'm going to be continuing the, oh, am I muted? Oh, no, I'm not. Okay. So I'll continue talking about enzymes. And when we consider an enzyme reacting with a substrate, we can say enzyme plus substrate with a rate constant for the forward and reverse reactions. And then you come out again with the enzyme unaltered, and then the product. The velocity of our reaction we can define as dp over dt, and that's going to be the rate constant for the forward reaction times the concentrations of substrate and enzyme. To measure initial velocity, we can measure the reaction rate during the initial period of the reaction. So that is before the substrate is depleted and before you get too much buildup of product. And if we graph the initial velocity versus substrate concentration, so this is going to be molar per second and this is molar, you can see where there's an asymptote, that's going to be your Vmax. And the concentration of substrate at half of the max velocity is going to be your Km. And so the reason that this plateaus here is at high substrate concentration, all your enzyme is going to be saturated, so the rate will not increase as you add more substrate. And at low substrate concentration, the rate is going to be proportional to the substrate concentration, so it's more linear at this part, and then it levels off. Okay, so this is enzyme catalyzed reactions, and then we can talk about this in terms of Michaelis-Menten kinetics. And so now we have the enzyme and substrate binding separated from the enzyme and product over here by the enzyme substrate intermediate. And so now we have the rate constant for the catalysis as well as the on and off rates for binding. And if the on and off rates for substrate binding are fast compared to the catalytic step, then the binding can be considered reversible. And so we have bidirectional arrows here. And we ignore the reverse reaction here because if we're measuring the initial velocity within a short time of mixing the enzyme and the substrate, then there's not enough product generated yet to drive the reverse reaction. Okay, so we can similarly write an equation for initial velocity dp dt, but this time it's with K2 and the enzyme substrate complex concentration. And so at steady state, we can get this equation for the enzyme substrate complex, and the change will be 0 because it's going to be constant, right? So the rate of formation, which corresponds to this term, and the rate of the dissociation of the enzyme substrate complex is captured by these two terms. And so when you add these up, it's going to equal 0. And that's because over time, the rates of dissociation and association of the enzyme complex will become equal. And so your free enzyme concentration and your enzyme substrate concentration will become constant. And so this is called steady state. So if we rearrange this equation here, we can get an expression for this here. And if we take our equation for the initial velocity again, then we can multiply this term by the by this rate constant. But free enzyme is not very easy to calculate, so we can rewrite it with E0, and that is our total enzyme concentration. And that's going to equal the free enzyme plus the bound enzyme. Or alternatively, you can write the free enzyme as this, so we can plug it back in. And another note here is that the substrate concentration it's so much higher than the enzyme concentration in the cell that basically the free substrate and the bound substrate is going to basically be your free substrate. So substituting that back in, so this term into here, and then we can rearrange more, and we get this term. And this grouping of rate constants here, we can define as Km, the Michaelis constant. So if we plug that into our equation, then this is what we get. And we can, again, use the equation for the velocity of the reaction to plug this in here. So multiplying by this rate constant. And then again, we can use the equation for Vmax. And so Vmax is going to be K2 E0 because when you have all the enzyme bound to the substrate is going to be the total. And what you wind up with is this equation here. And this is our Michaelis-Menten equation. And it makes sense with the definition of Km that we found earlier, because if you have the substrate concentration equal to Km, then you're going to get a 2 in the denominator. And so that's going to be 1/2 Vmax. Any questions on any of that? Okay. We can rewrite the this term again by saying that it's the fractional occupancy times E0, and then this is the term for the fractional occupancy. And if you remember from earlier in the course, this is how it's written with KD. And you can see that Km and Kd are analogous in determining how much enzyme is bound to the substrate, but they're not the same thing. So how are they different? Kd is for equilibrium state. Sorry, it's kind of blurry. And Km is for steady state. So your cells can be at steady state without being at equilibrium. And if we also look at the definitions of Kd and Km, or the equations, I mean. Km includes the rate constant for product formation, and Kd does not. So that's how they're different. And if K2 is much less than K minus 1, then Km is going to be approximately equal to Kd, right? Because then Km it will be like this because this term will go away if it's very small. And then if K2 is greater than or about equal to K minus 1, then you're going to get, sorry. So the substrate is going to be converted to product and released pretty frequently. And so the active site is going to be less occupied. So you could say that it's considered weaker binding. And to make this more clear with an example, if we look at binding equilibrium for substrate concentration equals Kd, the fractional occupancy is going to be 1/2 because we're not considering product formation here. We're just considering binding. But if we look at steady state, now we're looking at how the enzyme is forming product. And if you have a catalytic rate constant greater than the off rate, then your Km is going to be greater than Kd since the Km equals this, right? And so you have this larger term here. And so your fractional occupancy is going to be less than 0.5 as these are coming out more quickly. So yeah, that is one way how you can see that they are not the same thing. And going back to our Michaelis-Menten equation again, we have this, and for low substrate concentration, this term is going to be a lot greater than 1. And so the denominator here approximates Km over substrate concentration because it's so much greater than 1. And so our new equation for the initial velocity is going to be this. And we can rewrite this as this. And the reason we rewrite it this way is because this term right here, K2 over Km, is called our catalytic efficiency. It's basically telling you how effective is this enzyme, and it's the second order rate constant for the enzyme catalyzed reaction. And when you have high substrate concentration, this term is much less than 1. And so the denominator now becomes, it becomes 1. And then so you just get that the initial velocity is Vmax over 1. And so that's Vmax. And we can substitute this in again. And this is our catalytic rate constant. Kcat. And in Michaelis-Menten kinetics, Kcat and K2 are going to be the same thing. And so here the rate is independent of substrate asymptotically, and the rate constant at high substrate is when the reaction proceeds at the max rate. Okay. Any questions on this? Okay. So going back to catalytic efficiency, when you have a high Kcat over Km, that means that you have a very efficient enzyme. And as you approach the value for the rate constant of the diffusion limited second order reactions, the 10 to the 10 1 over molar times seconds, that's going to be a very good enzyme because you're basically only limited by how fast the enzyme and the substrate can collide in the correct orientation. Some enzymes are able to work faster than the diffusion controlled limit. One example is acetylcholine esterase. So acetylcholine is released by neurons to other neurons. So here's our synapse, and this is a positively charged substrate. So acetylcholine has to degrade, acetylcholine esterase has to degrade acetylcholine very quickly, because if it's not degraded, it can create effects long after the signal. And so acetylcholine esterase works faster than the diffusion limited rate. And there are electrostatic fields around proteins that can be polarized by charge groups, like from amino acid side chains and by the shape of the protein. Here I've drawn some electric field lines. And so the positive charges are going to go in the direction of the arrows. And so the red region is going to be negative electrostatic potential. And so it's lower energy for the positively charged acetylcholine to go here. And then the positive electrostatic potential repels the acetylcholine towards the active site. And so this is how that acetylcholine esterase can work faster than the diffusion limited rate, because it's funneling the substrates to the active site faster than diffusion. And one more thing, there can be different substrates for the same enzyme, and the reaction rate is going to be proportional to the kcat over km for each individual substrate. And so like if we have different peptide sequences, this one might have a high kcat over km, and so you're just going to get more. And this one, it's medium, so you get a little bit less. So the relative values of these catalytic efficiencies for substrates predict the relative amounts of the products formed. So if an active site prefers some specific amino acids, you might have a low kcat or a high km for the incorrect cleavage sites. Yeah, I think so. If there are any questions on that, that is all I have. And I have also posted a worksheet question. So, okay.
Okay, I'm just going to share my screen. Okay. So I'm going to be talking just about Lineweaver-Burke plots, and then also go back a little and talk about the K-on and K-off rate constants. But first, I'm just going to focus on Lineweaver-Burke plots. And so we just saw a really good presentation about the Michaelis-Menten kinetics. And these provide a really strong basis for doing graphical analysis of kinetic data for enzyme catalyzed reactions. And you can use like the data you collect and put it into computer programs, and they'll give you really good estimates for values of Km and Vmax, where you just kind of like list out all of your data points, and then it puts it in and gives you like examples and errors. But if we don't have a computer available, or like in the past, what they would do to analyze the data that we get from these kinetics is to rearrange the Michaelis-Menten equation and give a linear form. And this linear form is really easy to fit, and also it allows for pretty simple graphical analysis. So this is the Lineweaver-Burke plot, is the linearized form. And so it's created by inverting the Michaelis-Menten equations. And so you can see here is like the Michaelis-Menten equation, and then this is the Lineweaver-Burke. So you just divide by, or do 1 divided by, and it gives you these equations. And these are like these are both really important equations to kind of know. And like the more you work with them, the easier it will be to memorize them. And so does anyone like have a estimate or know what should be plotted on the x-axis and what should be plotted on the y-axis? You can like send it in the chat, or Okay, yeah, awesome. So for making this into like an equation, we need to make a plot. And so you're going to have the graph of 1 over V naught on the y-axis versus 1 over the concentration of the substrate on the x-axis. And this will give a slope, a line with the slope of Km over V max, um, a y-intercept of 1 over V max, and then an x-intercept of -1 over Km. And so you can like kind of just look at this equation and like using like the y equals mx plus b format, you can kind of figure out how we got all of this information. And just again, make sure to understand like these plots and also understand like all of these derivations because they'll be really useful for solving problems. And so if you like are given a plot, like you can always rewrite this and like try and figure out like what the x-intercept will be, what the y-intercept will be. But it's also kind of useful if you're taking like tests that are timed to just kind of have like this knowledge like packed away so that you can like just like solve these problems like a little bit quicker. And so this is what the plot will look like. And this is a Michaelis-Menten, and then this is the same data, but linearized and put into a Lin-Weaver-Burke plot. So you can see that the x-axis is the 1 over the substrate concentration with the y-axis being 1 over the rate, or V naught, and then the slope is Km over V max. And yeah, so you can see all the information from this. You can see how it kind of like adds up here. And so one question you might have would be like, why would we use these when we can do other sorts of analysis? And it's useful because you don't need to measure rates at high substrate concentrations to obtain Vmax values. So like you might think that to have like the maximum V, you'd have to analyze at a really high substrate concentration, but this kind of allows you to use other data to figure out what the Vmax would be. And this is good because some factors, such as the solubility of the substrate, can make it really difficult to measure rate at high substrate concentrations. Okay, and so now we're going to switch gears and talk about reversible reactions. And this is kind of covered in lecture 25 and lecture 26. So although we spent like a pretty good amount of time talking about like what we would call like a one-way reaction or just like the forward reaction, it's also important to consider the kinetics for reversible reactions. Talking about like one-way reactions only really works if the free energy change is really large. And so in that case, like the kinetics will be similar to like a reaction that only goes one way. But for a lot of reactions, the magnitude of free energy change isn't that large. And so both the forward and reverse reactions need to be considered if you want to actually analyze like, the kinetics of the reaction. Okay. And so we're just going to take this reaction, A giving B, B giving A. It's kind of hard to see, but this like top arrow has a Kf and this bottom has a Kr. And so this is just like a reversible unimolecular reaction in which molecules A and B are interconverting. One example you could think of would be just like a molecule switching from like a cis conformation to a trans conformation or something like that. And so Kf is the rate constant for the forward direction, and then Kr is the rate constant for the reverse reactions. And so we can determine the rate equations for these just as we would normally determine a rate equation for a reaction, except that because the reaction is going both ways, there'll be an extra term that accounts for the formation of A and not just a term accounting for like the disappearance of A. So that's what makes it different. And then you can see that these rate equations are given here, just the derivative of the concentration of A equals negative Kf A plus Krb. And then for change in B, it's Kf times A minus Kr times B. And so we know that A and B, we're going to try and like kind of simplify these, but also make them a little more complicated, I guess. But so we know that A and B are the only molecules involved in the reaction just because of the equation we're given. And so we know that the sum of their concentrations will have to be constant. And so we can like kind of set a variable x equal to the concentration of A plus B, knowing it will be constant throughout the entire reaction. And so we can substitute this equation into the differential rate equation for A, which is given here. And then if we integrate it, we get the following equation. And also you can do the same thing for B, but we just use A as an example. It's not super important, I don't think, to understand like the integration and stuff, but it is in the book in chapter 15 if you want like more details on how that's done. But so it gives us this following equation. And just so you know that AEQ is the equilibrium value of the concentration of A. And so the change in concentration is described kind of by a simple exponential function, which is different than you might think. But also it's important to remember that for reversible reactions, the concentration of the reactant won't be approaching 0. So in like a one-way reaction, you would assume that if this was just A going to B, you would assume that A would eventually approach 0. But because this is a reversible reaction, the concentration doesn't approach 0. Instead, it stops changing once the equilibrium concentration is reached. And so this kind of analysis is really important. And one practical implication is using it to determine how fast a ligand binds to a protein. And so this could be like a drug molecule or something else. And you can see how that might have importance in medicine or other fields. And so these reactions are bimolecular, which is different than the A to B reaction because it's the protein and ligand coming together. But we can simplify this analysis. And so to do that, we need to carry out the binding reaction in conditions where the concentration of the ligand is much greater than the concentration of the protein. And so if you think about it, if there's a way more ligand and very little amount of protein, even throughout the entire course of the reaction, the concentration of the ligand will barely change. And so this kind of makes it a pseudo first order reaction and allows us to kind of simplify our analysis. And so the binding reaction for the protein P and the ligand L is given as P plus L yields P dot L complex. And so this is K on the top and this is K off on the bottom. And so the K on and K off are the forward and reverse rate constants, just kind of like the KF and KR. When you're talking about protein ligand, K on and K off are the typically used terms. And so this gives us more kind of basic rate equations. And you'll see these are pretty similar to the ones we got for A and B reaction. And so I guess we can look at these and we know that L here is constant. And so we can try and take it out of the equation. And so we do that by setting K prime on equal to just K on times L. And so this allows us to rewrite the equations like this. And then we do the same substitution that we did to create this equation, but with these. And it gives us this equation for the concentration of P. And so P is the time-dependent concentration of the free protein. P naught is the initial concentration of the free protein, and P at equilibrium is the equilibrium concentration of the free protein when there's ligand present. And you can see it also includes the K on and K off. And so why is this useful? It's actually mainly useful for monitoring the binding of the ligand to the protein, so we can monitor binding and ligand and protein interactions. Often if fluorescence changes during the experiment, we can use fluorescent measurements to monitor this. And so then we can use rate constants, the parent rate constants that we derive for ligand bonding to derive the actual on and off rates by doing concentrations with varied ligand concentration. And then the professor goes over an example in the lecture 26 with the ABL system. Does anyone have any questions? I think I'm finished. Okay, awesome. We'll pass it to the next tutor.
Yeah, hi everyone. Just give me a second to share my screen. Can everyone see okay? Okay, I'll just assume everyone can see okay. So hi everyone, I'm gonna be talking about enzyme inhibition today. So I think this isn't a particularly difficult topic, but it's only confusing because a lot of different people have come up with a lot of different terms for the same thing. And sometimes it seems like you're dealing more, it looks like more than it is. So I try to, like, for the last 10 minutes, I kind of want to simplify things and kind of give you an intuition so that you can deal with different types of inhibition without having to memorize anything. So when you're given an inhibition, in order to really understand what it does, you have to answer 3 questions, basically. So does the inhibitor bind the active site, or is it allosteric? Does it like prevent the enzyme from functioning by binding to a different site other than the active site? Is it reversible or irreversible? Reversible meaning that it can bind with some like weak interaction and then dissociate, or irreversible meaning that it binds, let's say, to the active site and then forms a covalent bond that cannot be readily broken. And does it have a preference for the enzyme alone, so like just E, or the enzyme substrate complex, so the enzyme bound to the normal substrate? Because the inhibitor can affect the enzyme alone, it can bind to the enzyme and the substrate, or it can bind both. So these are the kind of things you have to consider when you want to determine the effects of the inhibitor. And then based on these, based on this information, we can kind of deduce the information about Km and Vmax. And so you don't really have to memorize anything. If you kind of remember these questions and you can define your inhibition, then you can really easily determine what the effect of inhibition is on Km and Vmax. So let's start with competitive inhibition, right? So I feel like it's really useful when talking about inhibition to write it out in sort of these reversible equations. So for this top left corner, what we see is, so the top line is just your normal Michaelis-Menten model, right? So you have your enzyme alone plus your substrate. You form this reversible enzyme substrate complex, and then through catalysis, in which the reverse reaction is so slow you ignore it, you recover the enzyme again, and then you get the product. But if you add the inhibitor, you can kind of view this as kind of depleting the enzyme. So you can kind of view this as a Le Chatelier equilibrium thing. If I add the inhibitor, I deplete the normal enzyme and I drive the reaction this way. Let's repeat, if you add the enzyme, you bind the free enzyme, you prevent the free enzyme from creating an enzyme substrate complex. And because you decrease this concentration, the equilibrium of this part shifts this way. So based on that, we can guess that in competitive inhibition, that the Km increases. So why does the Km increase? If ES is prone to dissociating into the enzyme plus the substrate, that means that there's less affinity, right? The substrate doesn't want to be with the enzyme. And Km you can kind of loosely think of as affinity, right? So the lower the Km, the lower the substrate concentration is needed to reach half of the maximum reaction velocity. So you have a lower Km, the enzyme has a higher affinity for its substrate than if you have a higher Km, which means that you need more substrate to reach the same threshold of half Vmax. And because it's competitive, just by the very name, you can kind of guess that if you add more substrate, you can outcompete the competitive inhibitor. This is because the inhibitor is one reversible and it binds to the active site. So let's kind of see what the Lineweaver-Burke plot looks like, which Ryan just told us about. So if we look at this, we see that the Vmax stays the same. So the y-axis is 1 over Vmax, or 1 over V. And we see that Vmax is the same, again, because you can always achieve the maximum reaction velocity by just loading your reaction with a bunch of substrate. But we see that Km on the a-axis increases because when you add a lot of inhibitor to the reaction, you sequester this, reaction is driven this way, so it doesn't want to associate as much. So then you get the effect where this is your Lineweaver-Burke plot for without the inhibitor, and with the inhibitor, it kind of like rotates clockwise around the y-intercept. So let's take a look at uncompetitive inhibition. And in your textbook, and I think in your lecture, it's referred to as substrate-dependent inhibition, which I think is a better name because the inhibitor only binds to the enzyme when the substrate is present. So we can do a similar analysis, right? So if the inhibitor binds the enzyme substrate complex, it prevents it from, it sequesters it in this form, and it prevents it from forming the product. So if we deplete this, the reaction is driven this way, and what the effect is, you actually get an increased affinity, right? So this always confuses me, right? Like, how is it that you add an inhibitor and you increase the enzyme's affinity for its substrate? Well, because by adding an inhibitor, you drive the reaction forward, only to this point though. So your Km decreases, again, Km being like indicative of enzyme affinity. But your Vmax decreases because if you add more inhibitor, you have less enzyme to work with and you produce less product. And this is not competitive because in uncompetitive inhibition or substrate dependent inhibition, the inhibitor binds to a pocket other than the active site, right? It cannot bind to the active site because the substrate is already in the active site. So by the very nature of this inhibition, we know that it has to be an allosteric form of inhibition. And then looking at the Lineweaver-Burke plot, we see that Vmax decreases, which we can see as the inhibitor, as the y-intercept moves up, right? Recall that the y-intercept is 1 over Vmax. So if I decrease Vmax, then the intercept increases. But Km decreases, right? Because your affinity is, your Km decreases because your affinity is increased, right? Because by depleting this, you drive the reaction forward. So then you see effectively the plot with the inhibitor is shifted left. And then for our non-competitive inhibition is this unique scenario where the inhibitor can bind both the enzyme alone and the enzyme with the substrate. So now, because it can bind both alone and it sequesters the enzyme in both forms, you don't drive the reaction one way or the other because the preference for the enzyme or the enzyme substrate complex is equal. So then Km stays the same, but you still see a reduction in Vmax because you're sequestering the competent form of the enzyme and you produce less product. And then here we see that, okay, Km stays the same, which is indicated by the same value of -1 over Km in our Lineweaver-Burke plot, but the y-intercept has shifted upwards, which, as we predicted, is correct. And that's really all it is for inhibition. So, I mean, people give a lot of different names and different terminology to kinds of inhibition, but just if you put it in this form and you think about inhibitors sequestering the enzyme, then it's really easy to figure out the relative affinities with or without the inhibitor. And if you think about whether or not by increasing the concentration of substrate, if you compensate for the reduction in enzyme activity, you can logically deduce whether or not Vmax changes. Does anyone have any questions?
Yeah, I have a question. For the top right case, for the uncompetitive one, is the binding irreversible for the inhibitor?
Regardless of whether it is, it can be either. So in this case, you can't tell from this diagram, which is like you correctly picked up. But the effect on Vmax and Km would be the same. So okay. Regardless of whether, because let's say that it was, say it was irreversible, then you sequester this, you drive the reaction forward this way, you still see the reduction in Km, and you still have less enzyme, so your Vmax goes down. If it was reversible, you still see the same thing. You sequester this, but even if you put more substrate, it's in a different pocket, right? So it's not competing. So you still see a decrease in Km and a decrease in Vmax. Does that make sense?
Yeah, that makes sense. Thank you.
Oh, sorry, guys. Does anyone else have any questions? Okay, if not, it was nice working with everyone.
All right, well, that's the end of our session for today. Yeah, like Nat said, yeah, it was a great semester. It was nice to work with all of you. And yeah, hopefully you enjoyed the course. I'm gonna end the recording now.